Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Make sure that I can see everything. Okay, exciting day ahead tomorrow. So let's actually just jump in here. So make sure I can see the chat. Okay, so there we go. So tomorrow you have your second test, and it pretty much covers everything up until what we did on Monday. So what we're talking about tonight will be, I guess, bonus material moving forward. And yeah, so just like last time, what I'll do is I'll give you guys an extra 15 minutes or so. So I will start the test around 11:15. I'm not factoring that time into the time that I would expect you to be able to finish the quiz in that time. So this is just an extra 15 minutes right off the bat, just to contend with any technical issues or any slowdowns in uploading that you might have. Other than that, it's pretty much the same deal. It's on Gradescope. It's going to feel almost like a quiz, except maybe a little more challenging, and you also have to upload your work for selected problems. Yeah, so
Sorry, what time did you say it was starting at 8:15?
Yes.
Okay, I just wanted to make sure I heard correctly. Thank you.
Yeah, so I'll give you guys a 15-minute head start, because I think a few of you have class very soon after. So instead of giving you extra time at the end, it's probably better that I start earlier. Yeah, so last time we started talking about, well, some motivations. So we learned about 3D space, and now we want to actually be able to do some more sophisticated things with 3D space. And it turns out that to be able to do these things, at least the things, yeah, so you're, as for the question in the chat, yes, you'd still log in, not with me, with Golek to be proctored. So we've been learning about 3D space, how to move around in 3D space, objects in 3D space, measuring vectors in 3D space, etc. And we want to be able to do some more sophisticated things like what we've been doing in calculus, finding integrals and derivatives and etc. And so that requires us being able to do certain things like describe a direction of slant in that space, as well as talk about the area of an object in that space, or the area of a patch, some sort of parallelogram or rectangular object in a space. Because then we know, using our calculus ideas, we can dissect any object into a bunch of little patches. And if we can find the area of all the patches, we can find the area of the object itself. So it became very important for us to be able to find area and things of that sort. So when it comes to that, finding the area of a patch, knowing the Are you guys seeing my screen moving, or?
No,
Hello?
I think there's a lag.
Yeah, because that seems very slow. I'm not sure what's going on there. Okay, so we're back, and okay. So last time we were talking about three-dimensional space and objects in three-dimensional space, vectors, all that good stuff. And we wanted to see if we could do some more sophisticated things in that space like we need to do with calculus. So we wanted to be able to talk about things like derivatives, in which case we would need something kind of akin to slope. Can I describe how things are slanted in space, what direction they're tilted in some sense? And we also wanted to be able to measure area of patches, right? So if we have an object and we want to find the area of that surface or that object in space, we dissect it up into little slices, objects running along the X and Y axis, and then we want to be able to actually find the area of these patches and add them up, right? And kind of do a Riemann sums idea. And yeah, so that's where we sort of were. And then last time we actually discussed how we would actually go about doing this. So to basically the area problem or the area issue, we got around it by saying, well, let's suppose that we could find the angle between the side of a corner of the patch. So we can describe the patch by vectors running along that the patch along its edges, and we can supposedly find an angle between them. Then we'd be able to find the area. So being able to find the angle of a corner of a patch was would allow us to find the area. The next thing that we looked at was how do we describe the direction in which something is slanted? And we saw that having something called a normal vector could actually get that done. So a normal vector was just a vector that is perpendicular, or the new fancy word is orthogonal. So that's the expensive word for that. And if we have some patch slanted in space, then we can describe its direction by finding some vector that is orthogonal to that patch, right? So these were the two things that we want to be able to find. Now, to be able to find an orthogonal vector, we're going to use a tool that we call the cross product. And to be able to find the area, or more specifically, the angle of a patch so that we can find areas, we're going to use a tool called the dot product. So that's where we are now. So that leads us to here, the dot product. And usually when someone introduces the dot product, they usually just jump right into the definition right here. But I'm actually going to justify this definition for you. And so you kind of see where this definition comes from, why it's actually important. We know now why it's important, because without this, we don't know how to find area, which is very important if we want to be able to do calculus. So let's actually see how this would be done. And I'm going to illustrate here with two-dimensional vectors. So these guys are in R2. But it's very natural how it would generalize to higher dimensions in this. So once you see me do it for R2, you're going to kind of understand how it would work for higher dimensions. So first things first, we saw last time that the law of cosines allowed us to be able to justify this equation. So we know that by the law of cosines, a minus b squared is equal to a squared plus b squared minus 2 times a times b cosine theta, where theta is the angle between a and b. Okay. And so what we're going to do now is I'm actually going to do some computations with this. So we know that what's this here is going to be a1 minus b1 comma a2 minus b2. And here I'm going to have a1 comma a2 and b1 comma b2. And these guys, I'm actually just going to leave the magnitudes written here. But everything else I'm actually going to expand and clean up. So we know how to find the magnitude of a vector. It's the sum of the squares of the components square rooted. And then now I'm taking a square, so all the square roots are going to be removed. So what we're going to get here is a1 minus b1 all squared plus a2 minus b2 all squared. Here I'm going to have a1 squared plus a2 squared. Here I'm going to have b1 squared plus b2 squared. And now what I'm going to do is I'm actually going to solve for Well, I'm going to bring things to one side. So let me move. This is going to be A1, B1 plus B1 squared plus A2 squared minus 2 A2 B2 plus B2 squared is going to be A1 squared plus A2 squared plus B1 squared plus B2 squared. Now I start simplifying, subtract. Notice that there's an A1 squared on both sides. I can subtract that. There's a B1 squared on both sides. I can subtract that. There's an A2 squared on both sides. I can subtract that. There is a B2 squared on both sides. I can subtract that. And then what I'm going to do is I'm going to just divide both sides by minus 2. And that's going to cancel the minus 2 over here. And on this side, what you're going to notice you're going to have A1 B1 plus A2 B2. And on this side, you're going to have the magnitude of that. Now, this is where something special actually happens, because it turns out that this guy here, which I'm now highlighting in green, it'll show up nicer on the white paper. It turns out that something like this guy always shows up when you flesh out this calculation. So in n dimensions, we'd get A1 B1 plus A2 B2 plus A3 B3 plus ... It'll go all the way up to AN BN. So what you realize is that this kind of expression here this is an important expression. And notice that that expression comes from the components of the vector. In fact, you see that it's just a sum of products where what is in the products is the corresponding components of both the vectors in the product. So notice here, I have two vectors, A1, A2, and B1, B2. What I did was I took A1 times B1 and added that to A2 times B2. So take the product of corresponding components and add them together. And you would realize that that kind of expression is very useful when you want to calculate the area. And because that sort of expression always shows up, it's a very nice pattern, we decided to give it a name. This, from now on, hence on, and forevermore, is known as the dot product of the vectors A and B. And we denote it by this expression here. Now, the dot is important. So it is important that you write the dot. You can't just write the vector A and the vector B just beside each other and not write anything in between them. You have to write out the dot, okay? So this is called a dot product. So if I'm given two n-dimensional vectors, A1, A2, all the way up to AN, B1, B2, all the way up to BN, they of course have the same dimensions, they're in Rn. Then we can define the dot product of the vectors A and B. We call this A dot B, and it's the expression A1 B1 plus A2 B2 plus A3 B3 going all the way up to A and BN. And so the notation we use for that is A dot B. And we actually say it like that as well, A dot B. So it's just a product of all corresponding components added together. And why would we come up with such a construction? Well, because it's useful to find the area because of the law of cosines. It's essentially why. You can also notice based on our derivation above, we can also describe the dot product in terms of the magnitude of the vectors in the product and the cosine of the angle in between them. And just to make sure that we all agree on which angle we're taking, when you have two vectors making an angle, there are two different angles that you can take. We are going to always define the theta to be between 0 and pi. And so the other angle will be the other part that adds up to 180. So yeah, that is the dot product. That's the definition. And where did it come from? Well, I just showed you. We wanted to find area, and by the law of cosines, this is what pops up. Another important thing I want you to note is that the dot product is a scalar. So I can take two vectors, two n-dimensional vectors, I can find their dot product, and the result is going to be a scalar. It's going to be a number. This guy here is not a vector. It's just going to be a number. It's going to be a bunch of numbers that I'm multiplying and adding together. So when I add them together, I get a number. So the output of a dot product is a scalar, and that output is actually very useful in finding the angle between the vectors and hence the area of infinitesimal patches. Another thing I want you to notice is that the dot product has these properties, which you can go through and you can actually just replace. Doing it in like 3 dimensions is going to be enough. You'll never need it beyond that. So you can replace A with A1, comma, A2, comma, A3 and write out these formulas, and you'll realize that all of these guys are the same. You will notice that the dot product is commutative, for example. So all of these things will be true. And this guy is messing up again. So you can see that the dot product is commutative. The dot product actually has a distributive law. So A dot B plus C, you can expand it. The zero vector dotted with anything is going to be the scalar 0, and so on and so forth. So all these properties hold. Another thing we can do is come up with another definition, and this is super important. So in terms of what you should remember, maybe I'll highlight those. I do expect you to have this memorized. I expect you to have this memorized. You should know that. And expect you to have this memorized. Okay, so remember the dot product is intimately acquainted with the area between the vectors. You'll notice that if theta, the angle between the vectors, you'll notice that if that angle is pi over 2, meaning 90 degrees, cosine of pi over 2 is going to be 0. And so you'll notice that when there's a right angle between your vectors, the dot product will be 0. So it turns out that the dot product is a very nice way for us to determine that two vectors are orthogonal, or they are perpendicular to each other. And that leads us to this thing that sometimes we define the dot product in this way, but we can think of it as a theorem or a proposition. A and B are orthogonal if A dot B equals the 0 scalar. Okay, so this is going to be some things that we are going to want to know, like this guy right here in this box, and I'll actually add a couple of things to this box later on. But now we're going to actually have ways, shortcuts of saying whether or not something is orthogonal to another thing, whether or not something is parallel to another thing. We already saw that parallel means one is a scalar multiple of the other. And now we have a new thing that identifies orthogonality, this very important property that we want to know about. Two vectors are orthogonal if their dot product is 0, the 0 scalar specifically. Okay. So let's actually do some examples. And this here, vector and scalar projections, we're going to skip this. It's actually very cool and it's remarkably useful, but it's not something that I'm going to want us to care about at this moment. You'll definitely see this in Calc 3. But for now, and you've probably already seen it in your physics classes for those of you taking physics, because a lot of things we've figured out in physics from projections. There are a lot of things in math as well, theoretically, that follow because of projections. However, we're going to do some more straightforward examples I expect you to be able to do. So like if I gave you two vectors, find the dot product or find the smallest angle between the vectors. Okay, so let's actually start off doing examples like that. So here's A. So if I want to find A dot B, and you have to write the dot. So this is the same as saying 1, 2, 3, dot product with 1, 0, -2. What is that? Product of all corresponding components added together. That's just 1 plus 0 minus 6, which is a -5. So that's it, the dot product of these two vectors, the vector 1, 2, 3, and the vector 1, 0, -2, the dot product is -5. And you might think, well, what does that number -5 mean? Or how would it be useful? Well, you'll notice the answer to that question hidden in part B. If we want to find the smallest angle between A and B, we know, or we know now, that our A dot B is equal to the magnitude of A, magnitude of B, cosine theta, where theta is the smallest angle between them. This means that your cosine theta is going to be A dot B divided by the magnitude of A, magnitude of B. And this would mean your theta is going to be cosine inverse of this. Okay, so now A dot B, we know what that is. That's -5. Magnitude of A, well, now we know how to do that since last class. It's going to be the square root of the sum of the components squared. Magnitude of B, that's going to be the square root of the sum of the components squared, which is 1, 0, and 2. So that's radical 14, radical 5. And so that's going to be cosine inverse of minus radical 5 over 14. So that's what we have. In fact, this is going to be, well, you won't have to know this. On a test or a quiz, that would be how you'd write your answer. But just for comparison's sake, okay, that is minus the square root of 5 divided by 14. Close parentheses, close parentheses. Is that 126.699 degrees? I'm not sure how to convert to go to radian mode on my phone. Well, if you had to do radians and you can't go to radian mode on your phone, you can multiply by pi over 180, and that would give you the radian measure. But yeah, that's it. That is your angle. So there we have it. The dot product is useful for this sort of reason. Do some more examples. Show that two vectors are orthogonal. Well, we now have a theorem that says two vectors are orthogonal if their dot product is 0. So all we have to do is show that the dot product is 0. So if I take, let's just turn that. So if I take 1, 3, 5, dot product it with -5, 0, 1, I would get 1 times -5 plus 3 times 0 plus 5 times 1. Well, that's just 0. Since the dot product is 0, the vectors are orthogonal. Right, and a 0 dot product is what tells you that. Here's another kind of question that could be asked. Find A dot B if you know the magnitude of A, the magnitude of B, and the angle between them. Well, again, we know that A dot B is equal to the magnitude of A, magnitude of B, cosine theta. So this is going to be the magnitude of A, magnitude of B, cosine pi over 4. So that's 2 times 3 times rad 2 over 2. 2's cancel. This is 3 rad 2. Okay, so these aren't so bad. So like once you know like what the formula is, you know these formulas, the problems at this level shouldn't trip you up too much. Suppose A1 comma A2 is a vector that's non-zero. Find a non-zero vector B that's orthogonal to A. Many I don't know what's going on today with all the technical difficulties. Everything was working fine earlier. I don't know what's going on. Now this guy's lagging. In the meantime, any questions so far? Talk to myself.
I don't think so. I think we're good.
This one is actually just an excuse for me to show you a neat trick. So the idea is, if you're given A1 comma A2, you can always multiply by something like the following. You can swap the coordinates if you're in 2 dimensions, and then you make one of them negative. So B equals this guy would work. So that you'll notice would give you not a vector. It would give you minus A1, A2 plus A1, A2, which is always going to be 0. Or another way you could have done it, if you want to make sure you have a non-zero vector, again, you could switch them. But make the negative in the second component. So B, and because B has the components of A, and we know the components of A are not 0, B is not 0 either. So B equals minus A2, A1 works. So does A2 minus A1. And I just wanted to show you that because there are some other derivations where there comes a point where you make certain choices, and a lot of times the book is going to pull a vector out of thin air and say, oh, we can use this vector to do that. And I just want you guys to appreciate that what they're really doing is that they're just manipulating the components and changing the signs so that they can get a dot product to be 0 or something like that. And they can actually force something to happen, right? So they can come up with a vector at random, well, not quite at random, that they can know is orthogonal to another vector. Of course, in 2D, you can do this pretty much uniquely. So in 2D, these are pretty much the only 2 answers that I could come up with that have these properties, you know, up to that has these properties up to scaling pretty much. When you go to 3D, though, there is many other ways, because we know that once orthogonality in 3D is a lot more complicated in the sense that you can have a lot more directions being orthogonal. But it's a kind of game that we can play. And we'll stop there. So that's all we need to know for the dot product, really. So the dot product, what you need to remember, that's the definition. This is a consequence of how it's constructed. Dot product is a scalar, very important that you know that. As well as dot product equals 0 means the vectors are orthogonal. So if you want a quick check as to whether 2 vectors are orthogonal, you can just actually take their dot product. And of course, these are just some straightforward calculations that you can do. And you can actually use these calculations to do a whole sorts of things. For example, like projections, figuring out if you projected the shadow of one vector onto another, what would be the length of that shadow? If you wanted to project the shadow of one vector to another and then create a vector running along that shadow, it turns out you can use dot products to do both of these. And these guys are called projections. And it's actually a very important thing to be able to actually do for various reasons. But we're not going to go into that. What I basically want you guys to know is what a dot product is, how to actually calculate it, and what are some of the things you can use a dot product to determine. Namely, at this point in time, the most important for us is the angle between the smallest angle between 2 vectors and whether or not they are orthogonal. So that is the dot product. Moving on to the next guy. And today is not the 7th. A is the third. So now we're going to talk about the cross product. And the point of the cross product is to tackle the other thing. So last time we realized that we can talk about the direction in which something is slanted by determining a vector that is orthogonal to that thing, because there's some sort of uniqueness that is associated with being orthogonal that is not associated with any other meeting at any other angle. So this now is what we're going to tackle. So I think I can make this a little bit larger. So this is what we're going to tackle. And just as how we use something called a dot product to tackle the angle problem just now, we're going to use another kind of vector product to tackle the orthogonality problem. So at this point, the cross product is more, and this is how it was naturally developed as well. Well, it kind of developed for various ways. But the cross product, it's easier to develop that guy kind of in hindsight. So you pretty much say what kind of vector you want, and then we're going to figure out how would we construct such a vector. And here's how we define the cross product. And this is not the definition that I would say you have to remember. I'll get to that definition pretty soon. But here's how we're going to do it. Given two vectors in 3 space, right? So this definition is for 3 space specifically, and I'll talk a little bit more about that in a little bit. So vector A and vector B, A1, A2, A3, and B1, B2, B3. We define the cross product. We call it A cross B, and the notation is A with an X and a B, and it's very important that you write that X as opposed to a dot. So when you write the X between vectors as opposed to a dot between vectors, it means a different thing. When it comes to numbers, they both mean the same thing. But when it comes to vectors, it's something completely different. So A cross B is the vector, this vector, where N is a vector that's orthogonal to A and B at the same time, okay? So what is that saying? Well, when I say I want to find a cross product of 2 vectors, I want to find a vector that is orthogonal to 2 other vectors. However, I want that vector to have a certain magnitude. I want the magnitude of that vector to be magnitude of A, magnitude of B sine theta, right? So if I have a vector that is orthogonal to both A and B, and it's a unit vector, I can multiply it by a certain magnitude to create a cross product vector. So a cross product vector is going to be a vector that is orthogonal to a patch or a plane, that it has a very specific magnitude, namely this magnitude. And if you're wondering where that magnitude comes from, why it looks familiar, well, that was what we saw last time. I believe it's on the last page. Last time, we saw this guy, AB sine theta. So what we want is we want a vector that is orthogonal to 2 other vectors, and we want the magnitude of that vector to be equal to the area spanned by the 2 vectors. Okay, so this is what we want. And again, there are various reasons as to why we would want that lie in physics and more realistic stuff, but I don't want to actually get into that. But this is the vector that we want. This is the vector that we're searching for. I want a vector that's orthogonal to 2 other vectors of a specific magnitude. Now, again, a motivation as to why we'd want a specific magnitude and why it would kind of come up with a sine versus a cosine and all that stuff. You can check out this link if you're interested, but we're not gonna worry about that, and I'm never gonna actually test you on any of that. One thing I do want you to notice is that the cross product is a vector, as opposed to the dot product. So the dot product is a scalar. If I take 2 vectors and I find their dot product, the result is going to be a scalar. However, if I take 2 vectors and I find their cross product, the result is going to be another vector. So that's one thing I want you to note. Another thing I want you to note is that the notion of a cross product, like we're using it, only really makes sense in 3 dimensions. A cross product in 2 dimensions isn't really useful. It's actually a scalar, a 2-dimensional cross product, but it's not as useful as a dot product. So we kind of ignore it. As well as for anything higher than 3 dimensions, the cross product is a special case of something that's called a wedge product, which is, again, way above our pay grade. We won't need to worry about anything that complicated. So whenever I say a cross product, I am specifically talking about, and anyone else who's talking about it, it's 3D specifically, 3D only. Right? So if I give you 2 4-dimensional vectors and ask you to find a cross product, it doesn't mean anything. That's meaningless, right? Give you 2 vectors in R2, ask you to find a cross product, doesn't mean anything. The vectors have to have 3 components. Here's another thing. Notice that if your theta is 0 or pi, because of the sign here, sine of 0 or sine of pi, that is going to be 0. And so what you get is you get a 0 scalar times a normal vector, which gives you a 0 vector. In other words, the cross product provides a way to talk about something being parallel. If the angle between the 2 vectors is 0 or pi, which means they are parallel, they either run in exactly the same direction or exactly opposite directions, then your cross product will give you a 0, which is one of the reasons why we want the sign here, why we want this particular kind of construction. And so it's even better than the last double box that I gave you guys in the last one. So these are this is very important for you to know. Okay, so when we have vectors, it is very often going to be very important for us to recognize whether 2 vectors are orthogonal or whether they're parallel or neither. And now we know 2 vectors are orthogonal if their dot product is the 0 scalar. And this works for any dimension. As long as A and B have the same dimensions, the same number of components, this will work. A and B are parallel if one vector is a scalar multiple of the other. And another way to say that A and B are parallel is if their cross product is a 0 vector. So this is specifically if we're in 3D. Another way of saying that, if A and B are 3D vectors, if the magnitude of their cross product is a 0 scalar in 3D, then that's another way to determine that they are parallel. So if I take 2 vectors and I find their cross product and that ends up being the 0 vector, I know that those 2 vectors are actually parallel. And so, yeah, I can do that. Or if I know that the magnitude of the cross product is 0, it means that the vectors are parallel as well. So we now have, in terms of vector products, a way to determine whether things are parallel or whether things are orthogonal. And that's actually very useful. It's a very useful thing computationally and theoretically and conceptually. It's really important for you to know this this box here. I cannot stress that enough. Know this. Okay. Now, another thing that you'd want to note is that there are actually 2 ways that you can be orthogonal, which we spoke about last time. So if I have a vector A here and a vector B here, notice that there are 2 ways that you can be orthogonal to both at the same time. You can be orthogonal but pointing up, or you can be orthogonal and pointing down. And up and down, of course, is relative, but you get what I mean, right? So you can be pointing in this direction or exactly the opposite direction. And how we determine which direction that we are pointing in, just for the sake of it's actually a convention, right? By convention, we determine the cross product by the vector that follows what we call the right-hand rule. So at this point, a lot of you would already know about a right-hand rule from Calc 1, which is when we were doing Riemann sums, and we're taking the right-hand sums. Not that right-hand rule. Some of you are already also aware of right-hand rule in physics, where it's talking about magnetic fields and electric fields and how they relate to each other. Not that right-hand rule either, right? If you want to know about the right-hand rule from physics, that's the link here. You can find it there. But this is a whole other right-hand rule. This is a rule that deals with the direction of the cross product specifically. And the rule works as follows. if you want to find A cross B, you would point your index finger in the direction of A of your right hand. It's very important that you notice that this is the right hand. Point your index finger in the direction of A of your right hand, stick out your middle finger orthogonal to that, and then stick your thumb up. Your index finger goes in the direction of A, your middle finger goes in the direction of B, your thumb is the direction of A cross B. Another way you can think of that, according to this picture over here, is to use your entire right hand. Point your entire right hand just flat out in the direction of A, curl your fingers in the direction of B, and stick your thumb up like a thumbs up. And the direction of your thumb is the direction of A cross B. So what you'll notice here is that in this diagram here, if I were to, stick my right hand, right? So if my fingers were directly pointed out, very straight, they go in the direction of A. My fingers are going to curl along my right hand towards the B. And then when I stick my thumb up, that is the direction of A cross B. Okay, so hopefully you got that. So as this is sketched, which one of these guys is A cross B? Is it the guy on top or the guy on the bottom?
Wouldn't it be the one on the bottom?
It will be the one on the bottom. So according to this is A cross B. So what would this guy be up here?
B cross A.
It's going to be B cross A. Can you tell me what that would be in terms of A cross B? How does that relate to A cross B?
Would it just be negative A cross B?
It's the negative of A cross B. Okay, so it turns out that the direction of your cross product actually matters. And if you're going in the wrong direction or the opposite direction, what happens is it negates the cross product of the other direction. Now, there are a couple things that are important here. One, you will notice that the cross product is not commutative. So A cross B and B cross A, they are not the same thing, right? The dot product is commutative. A dot B is equal to B dot A. However, A cross B is not equal to B cross A in general. In general, A cross B is actually the negative of B cross A. So commutative of the product is not true for the cross product. It holds for the dot product, but it doesn't hold for the cross product. And so that leads us to these sets of rules here. You'll notice, for example, 1 says that A cross B is not B cross A. In fact, 1 is the negative of the other. So this kind of highlights something that I mentioned last class, how there are times when I would write down these properties, or any math teacher is going to write down these properties where you're going to like, well, isn't that obvious, right? So there were times where over here, like with the dot product, when I was writing down those properties, because we call it a product and we're used to writing dot to mean multiplication of numbers, it seemed kind of obvious for me to say, well, oh yeah, A dot B is the same as B dot A, because we're in this kind of conceptual realm where we're used to multiplication being commutative. Or even prior to that, where did I do that? Yeah, so things like this, A plus B equals B plus A, and we'd write things down like this, and a lot of times students just, it goes over their head. They just think that we're wasting time saying all these things, because isn't it obvious? Of course, if you're adding them, you can add in either order, or if you're multiplying them, you can multiply in either order. This is one of the first non-trivial cases in mathematics, I think, where most people would realize that, yeah, all those nice rules that you know about commutativity, associativity, you've been taking them for granted all this time. So all those rules that you notice with the real numbers that are very nice, they don't always hold. It's not always true. And so there are going to be times when we're going to give you properties where, on one hand, because you're used to working with real numbers, it would seem obvious, but on the other hand, it's actually not, because the real numbers are a very peculiar set. And when it comes to like sets of vectors, things can be different. And when it comes to other operations other than multiplication of real numbers, they can be very different. So the cross product is what we call a product, but it doesn't behave like the product of real numbers. And here's one way in which it's very different. Another way it's different is it's also not associative. So if I take A cross B cross C, it's different from taking A cross B cross C. And again, that's something that with addition and multiplication wouldn't have made a difference between real numbers. However, with vectors, the cross product is very different. The cross product does distribute across sums, as you see here. But again, on the right side, the A cross B is very important that you have it in that order. So it's very important that you notice order matters. So A cross B is not the same as B cross A, right? So whenever you're multiplying things out with a cross product, it's very important that you pay attention to the direction in which you're multiplying things out. Who was on the left, who was on the right? Because whoever is on the left needs to stay on the left. In rule 3, you'll notice on the left side, the vector A is on the left. Therefore, on the right side, when you expand, the vector A needs to remain on the left. It's actually very important. If you get sloppy and you put the A on the right, you have now gotten the problem wrong, right? So yeah, so there are going to be times when we're going to write down properties like this, me or some other professor, and on one hand, you're going to be like, well, isn't that obvious? But it's not obvious. Whenever someone takes the time to write something like this down, where it seems like totally blindingly obvious, it's usually not obvious. Because especially at this level, when you're in college, everyone's always rushing to finish the syllabus. We're not going to waste time and talk about things that we don't really need to talk about. So yeah, the properties are important. So when it comes to the cross product, this is the guy that we actually want. We want a vector that is orthogonal to two other vectors, right? So this is it's at right degrees to, at a right angle to B, and it's at a right angle to A. Maybe I'll use a different color. It's at right angles to B, and it's also at a right angle to A. And at the same time, if I were to create a parallelogram with A and B, the area of that parallelogram is the same as the magnitude of the cross product. So the length of here, the magnitude, equals the area of the parallelogram. Okay, so this is the vector. So I'm telling you about the concepts behind a cross product. So I haven't even told you how we're going to find one yet, but I'm telling you what it is, how it's supposed to behave, because that's actually pretty important. And that's going to be super important in all your future classes from now on when you're doing any sort of math in multiple dimensions or any sort of calculus in multiple dimensions. The idea of a cross product is going to be very important, and how it relates to objects in that space is going to be important. So a cross product is a way to get an orthogonal vector that points in a direction that is consistent with the right-hand rule, and the magnitude of such a vector will be equal to the area of the parallelogram spanned by the two vectors that created the cross product. The cross product is a vector, it is not a scalar. The cross product is going to be a way that, given two vectors in three-dimensional space, I can find a third vector that is orthogonal to both of those vectors at the same time. The magnitude of that vector is going to be equal to the area of the parallelogram formed by the two original vectors, and it will point in a way that is consistent with the right-hand rule. And the right-hand rule, why we care about the right-hand rule is, again, it goes back to physics. Because of a lot of things with electromagnetism, how things behave in reality follow the right-hand rule. And so that's why we chose, by convention, the cross product to behave in such a way that it is consistent with the right-hand rule. This is not listed in the properties, but you should be able to take it for granted. Cross-producting with 0 gives you the 0 vector. So A cross the 0 vector is going to be the 0 vector. 0 vector cross A is going to be the 0 vector. The property 5, this one here, is called the scalar triple product, or the scalar box product. And what that is useful for is if you have 3 vectors, A, B, and C, and they run along the edges of what is called a parallelepiped, then this kind of calculation, A dot B cross C, actually will give you the volume of that parallelepiped. And so that's actually very intimately acquainted with not only a cross product, but also with something that's called a determinant, which we're going to talk about later. Yeah, so we're going to do that calculation, but I don't really expect you to know a lot about that right now. Property 6, by the way, is also a nice property, which again, we're not going to get into. It's called the vector triple product, and it's actually used in Kepler's law on planetary motion, among other things. So this is really important stuff that we're glossing over here. But at this point, you're in Calc 2. I really expect you to have the basic concepts down and be able to do the basic calculations. So now let's talk about how we would compute the components of a cross product. So let's say I have 2 vectors and I want you to tell me the specific vector, as in tell me the I component, the j component, the k component of the cross product. How would you actually do that? Well, that's what we're going to figure out now. And that's what I'm going to derive for you guys now. So ultimately, I'm going to tell you how you're going to come up with a cross product. And then we're going to stop there. And I'll leave some examples for you guys to actually do of computing cross products, which would be useful for our class next week, as well as in the bonus in the test, right? So if I actually compute a cross product as a bonus in the test, you'll know how to do it. So basically what we're going to do is we're going to make sure that we're going to construct an orthogonal vector that behaves in the way that we want. Now, because of last time I showed you that we can write any vector in terms of I, j, and k, the vectors I, j, and k, it stands to reason that if I know how the cross product deals with I, j, and k, I can kind of figure out how it's going to deal with any other vector. And this is why they're called basis vectors, right? They're the basis for a lot of calculations. So if I want to know about how vectors will behave, a lot of times I can just look at how they treat I, j, and k. They're sort of like the prime numbers for numbers, right? So there are a lot of things in number theory that we figure out by figuring out how they deal with prime numbers. And because all other numbers are constructed based on products of prime numbers, knowing how the things deal with prime numbers, we can figure out how they will deal with general numbers. We're going to do the same kind of idea here. So you can think of like the prime numbers as a basis for all integers, and ijk is the basis for all 3-dimensional vectors. So if you know how to deal with those guys, we can figure out how to deal with everyone else. So here's the principle. The principle is a circle. So you can have this circle here, and ijk going around clockwise. Notice that if you take any 2 things going clockwise, so let's say I'm moving in this direction here, I cross j, the result is going to be the next guy, k, right? Or if I take j cross k, the result is going to be I. If I take k cross I, the result is going to be j. And this is just a mnemonic to remember the right-hand rule. So for example, in the right-hand rule, if I point my right hand in the direction of I, curl my fingers in the direction of j, and put my thumb up, that will go in the direction of I cross j. And you will notice that that is actually equivalent to the direction of k, right? So if I point my right hand along the x-axis, curl it towards the y-axis, stick my thumb up, my thumb will be pointing in the direction of the z-axis, right? And so I can figure out that I cross j is k. Similarly, I can just move my right hand all over the place in various different orientations and figure out all these other guys. Once I do that, I know all of these guys, and a mnemonic for remembering that is this circle. If I go the opposite direction, like counterclockwise, like J cross I, the result is going to be negative K. So when I'm going counterclockwise, I get the negative of the cross product. So that's like this one here. J cross I is negative K. So that's going to be useful. Okay. You can also realize these facts here. I cross I is going to be 0 vector. J cross J is going to be the 0 vector. K cross K is going to be the 0 vector. Why is that true? Because we learned earlier that whenever two things are parallel, the cross product is going to be the 0 vector. So I is, of course, parallel to itself. J is parallel to itself. And K is parallel to itself. So all of these guys, if I cross them with themselves, they're going to give you the 0 vector. If you cross a vector with itself, you get the 0 vector. Okay. So now let's actually figure out the cross product of vectors. How do we actually do it? And by that I mean, tell me specifically how to find the vector that does that property for two given vectors. So let's say I'm given vectors A and B, A1, A2, A3, and B1, B2, B3. And I want to find A cross B in terms of the components. Here's what I have. I have A1I plus A2J plus A3K times, well, not times, cross product with B1I plus B2J plus B3K, and using the properties that we had earlier about the fact that the cross product actually multiplies out, there is a property 3 here. We can actually expand the parentheses. So what we would get is we would get something like A1 B1 I cross I plus A1 B2 I cross J plus A1 B3 I cross K plus A2 B1 J cross I, A2 B2 J cross J, A2 B3 J cross K, and we'll just keep going. A3B1 K cross I, A3B2 K cross J, and A3B3 K cross K. Now we apply what we learned just above in this mnemonic. I know that K cross K, that's 0. J cross J, that's 0. I cross I, that's 0. Also, what we know is I cross J is actually K. So this is K. I cross K, well, this is going to be minus J. J cross I, this is going to be minus K. J cross K, this is going to be I. K cross I, this is going to be J. And K cross J, this is going to be minus I. So now I'm actually going to group like terms. So I'm going to have a bunch of things times I, a bunch of things times J, and a bunch of things times K. And there's a reason why I'm leaving the negative here but we'll see that later, why I left the negative there. So who are the i's? The i's have it. So for I have A2, B3. A2B3 minus A3B2. I have for the J, and I'm factoring out the negative. So this is A1B3 minus A3B1. And for the K, I would have A1B2 minus A2B1. And that is the cross product, very specifically in terms of two vectors. And so, yeah, that leads us to essentially this guy. So this means A cross B is going to be equal to, well, this guy. So I found the specific vector that does exactly what we want. This will obey the right-hand rule, and I know that because of this thing that we figured out here. And it also will give us the orthogonality principle because of the properties that we had here. So this particular vector will do what we want. Which is nice. We now know how to find the cross product. So of course, just like how you have to memorize the definition of the dot product, you have to memorize this. And it turns out that you could memorize it. There's nothing wrong with memorizing that, actually. But I didn't memorize it, and a lot of other people don't memorize it. There's actually a mnemonic here. There's a shortcut for remembering how this actually goes. And that's why the shortcut is going to give you a negative sign in the middle here. And so that's why I wrote it in this particular way. Now, for that, you're going to have to remember how to find determinants of matrices, specifically of 3x3 matrices, which I think a lot of you guys know. So I'm going to really rush over this in the last few minutes. Yeah, I mean, you can read slowly and figure out what I did after the fact. You're not going to have to know what a determinant is really, but just so that you have the names and you sound like you know what you're talking about when you're talking about these. So matrix is a rectangular array of numbers. We can call a matrix by the number of rows by the times the number of columns. So for example, this is a 2x2 matrix, whereas this is a 3x3 matrix, right? This is a 2x3 matrix. So these are matrices. When a matrix has the same number of rows and columns, we call it a square matrix. And for square matrices, you have something that's called a determinant. Now, determinants are defined well, based on volume, actually, but they're recursively defined based on the following idea. A 2x2 determinant is defined by this equation right here. So you literally take the product of the guys along this diagonal, and then you minus the product of the guys along that diagonal. So yeah, if I want, didn't want to. So if I wanted to find, for example, the determinant of 1, 2, 3, what I would do is I would take 1 times 4 and then subtract the 2 times the 3. So that's going to give me 4 minus 6, which is minus 2. And that's going to be the determinant of the 2x2. And that's it. You don't have to know what that means. Technically, it's going to be, right, if you had A here and B here, then the area between A and B area is going to be actually given by the magnitude of minus 2, where the A is the first row and the B is the second row. So it's intimately acquainted with geometry. There's a reason, right? The same way like dot product and cross product, it was all about geometry, me finding areas and directions. So the determinant is actually defined for that reason as well. So now for the 3x3 determinant, the idea is, can we figure out a way to get the volume of the vectors? If I have one vector A, comma B, comma C, another vector D, comma E, comma F, another vector G, comma H, comma I, put these guys together to create a parallelepiped. How can I find the volume? Well, you find the 3x3 determinant, and the magnitude of that is going to be the volume. Now, I'm going to show you the quick way to do that. There are many methods to do this, but probably the best method is going to be Laplacian expansion. Now, it's worth mentioning that you can do Laplacian expansion along any row, but for our demonstration purposes, we're going to be doing Laplacian expansion along the first row. You always have a plus sign attached to the top left. And you alternate signs otherwise. So the B, you will take with it a negative sign. The C, you would take with it a positive sign. You would have taken with this a negative sign, taken with this a positive sign, etc. Right? And here's how it's going to work. So to get the 3x3, what you're going to do is you're going to put positive A, whatever number is there, you're going to multiply by a 2x2 determinant. Minus the sign for the B, you're going to multiply by a 2x2 determinant. Plus the sign for the C, you're going to multiply by a 2x2 determinant. And not being in person is going to be very, I would usually like put my arms up on the board and show you how to find these guys, but not being in person, it's kind of hard to show you how to do that. So what I'm going to do is I'm going to have to, I think, sketch this out. So where does the 2x2 determinant for the A come from? Well, you move to the A in your matrix. You block out everyone in his row and his column. The matrix that is left over is the 2x2 matrix that goes in there. So here you'd put E, F, H, I. Similarly, when it comes to the B, you're going to imagine that you blocked out everyone else in his row and his column. The matrix that is left over, that is the guy that goes in there. So here you would get the D, F, G, I. And for the C, you do the same thing. Block out everyone in that row and that column. You'll have a matrix left over here. And that's the guy that you put in here. So here you would get the D, E, G, H. And then you do the 2x2 determinants, right? So ultimately now you get equal to A, and you're going to do the EI minus FH. Minus the B, and you're going to do DI minus FG. Then you're going to do the C, which is DE, DH minus EG. And that is going to be the 3 by 3 determinant. And that's why I wrote it with a negative sign in the middle, just to match up with this construction. Now, why did I go through and show you that? Well, let's just do an actual quick example. So here, if I want to expand along the first row, it's a positive sign here, negative sign here, positive sign here. This is going to be positive 1 times 3, 1, 1 minus 1 minus a negative 1 times 0, 1, 1 minus 1 plus a positive 2 times 0, 3, 1, 1. Then I do the 2 by 2 idea here. So multiply this by this minus that by that. So this is going to be 1 times 3 times minus 1 times 1 plus 1 times 0 times minus 1 times 1 plus 2 times 0 times 1 minus 3 times 1. So this is going to be minus 3 minus 1 minus 1 minus 6, it looks like. Minus 11. I think that's what we should get. Kind of rushing because I know we're over time. But is that kind of clear, like how we would find the 3 by 3 determinant?
Yeah, it makes sense.
Okay. Now, why did I show you that? Because that's actually a shortcut to figure out the formula for the cross product. It turns out the cross product of A and B, you can think of it like this. You can think of it as a 3 by 3 determinant, where across the first row you put I, J, K. Across the second row you put the coordinates of B, of A, and across the third row you put the coordinates of B. So if I wanted to find A cross B, I think of this as I, J, K. A1, A2, A3, B1, B2, B3. And it turns out when you do this often enough, you'll get actually very quick at doing this in your head. So it's almost not even worth memorizing the formula, because you'll get so used to the construction by muscle memory. But yeah, so what you're going to do is you're going to have plus I minus J plus K. So for the I, you're going to block out everyone in that row and that column, and then you're going to do the cross product kind of thing. A2 times B3, A3 times B2. A2 B3 minus A3 B2. Then same thing for the J. Block out everyone in that row and that column. Then you're going to have the A1 B3 minus the A3 B1. Then the same thing for the K. You're going to block out everyone in that row and that column. You're going to have the A1 B2 minus the A2 B1. And this is what we got before. So it turns out that the finding a 3 by 3 determinant actually functions as a mnemonic to remember how to find the cross product of two 3-dimensional vectors. So what I will do is I would leave some examples for you guys to do for next time. But right now we're going to stop there. So I gave you the general formula of how to find a cross product. And at this point, we now know what a cross product is. So given two vectors in 3 dimensions specifically, if I want to find a vector that is orthogonal to both vectors, whose magnitude is the area of the parallelogram formed by those vectors and who follows the right-hand rule, this is how you would do it. It's this vector right here specifically, right? And yeah, that's where we are going to wrap up. So you can actually do this, like finding a cross product or finding vectors orthogonal to two other vectors and things of that sort. You can do some practice with that, which of course I will do that with you guys on Monday before moving on to the next section. So you guys can try to do that. I'll leave these in the notes for you guys to try, but for now we'll wrap up there. And yeah, the plan was to actually finish on time today because I know you guys have a test tomorrow, but the technical difficulties kind of slowed everything down. But hopefully that was clear. If you feel like your head is spinning, don't worry about it. You don't need to know any of this for the test. It would be, if you want a little extra icing on the cake, you can do the bonus problems with what we learned tonight. And so that being said, I think we are going to stop there. So hopefully you guys followed along. And if you have any questions, of course, you can let me know. Although I wouldn't have any questions on this before tomorrow because it's not that important. But next week, you guys can let me know. But yeah, I'll let you guys go. Thank you for your attention and your patience with all the technical difficulties. We are going to stop right there. I will see you guys in the next one. Ciao.